Hello everyone and welcome to this explainer. Today, we are going to completely break down Chapter 9 of your Class 10 science textbook, Light, Reflection, and Refraction. Now, I know physics can sometimes seem a little intimidating, right? With all those complicated diagrams and formulas, but honestly, we've totally got this. Let's take a journey together to really understand how light behaves when it bounces off surfaces and when it bends through them.
Okay, so here's our roadmap for today's session. We're going to logically step through this, starting with spherical mirrors, mastering those ray diagrams, tackling the mirror formula and magnification. Then we'll shift gears into refraction with the glass slab, understand the refractive index, and finally bring it all together with lenses and lens formulas.
All right, let's jump straight into part 1, Spherical Mirrors Explained.
We're going to start our journey with something deeply familiar. Looking at our own reflection. To really understand spherical mirrors, just imagine grabbing your shiny, everyday breakfast spoon. That part that holds your cereal, the surface that curves inwards, that is your concave mirror. Now just flip the spoon around. The back part, the one bulging outwards, is your convex mirror. It is genuinely that simple. Think of a spherical mirror as just a slice cut out from a hollow glass sphere. If the reflecting side faces the inside center, it's concave. If it faces the outside, it's convex.
Before we can draw anything, we need to set up our mental whiteboard and define our core vocabulary. First up, the pole, represented by the letter P. This is the exact geometric center of the reflecting surface itself. Now remember that imaginary hollow sphere the mirror was cut out of? The very center of that imaginary sphere is called the center of curvature, or C. The distance from the pole to this center point is your radius of curvature, R. And finally, imagine a straight highway passing directly through the pole and the center of curvature. That is our principal axis.
Now here is a really fascinating concept, a special point called the principal focus, or F. If you shine rays of light completely parallel to the principal axis onto a concave mirror, they all reflect and crash together into the single intersecting point. And what's super convenient is that this principal focus sits exactly halfway between the pole and the center of curvature. Because it's perfectly in the middle, the radius of curvature is literally just twice the focal length. Mathematically, we just say R equals 2F.
Moving right along to part 2, mastering ray diagrams.
So this is the part that usually scares students. But let me tell you a secret. Ray diagrams, they are just simple geometry games played with 4 basic cheat codes. Cheat code number 1, any ray traveling parallel to the principal axis will always pass through the focus after it reflects. Number 2 is just the exact reverse. A ray passing through the focus reflects out parallel to the principal axis. Number 3, a ray passing through the center of curvature hits the mirror straight on at a 90-degree angle, which means it bounces right back along the exact same path. And number 4, a ray striking the pole at an angle just reflects back at that exact same angle, obeying your basic laws of reflection. Memorize these 4 moves and you are unstoppable.
Those 4 rules are your universal language for mapping reflection. To figure out exactly where an image forms, you literally just pick any 2 of those 4 rays, draw them from the top of your object, and see where they cross paths after reflecting. Just keep one huge difference in mind. Because a convex mirror bulges outwards, its center of curvature and focus actually hide behind the non-reflecting side. So the rays don't physically pass through the focus, they bounce off and just appear to spread out or diverge from that point behind the mirror. Let's look at how this all comes together for a concave mirror. There is a beautiful, predictable pattern here. Imagine moving an object closer and closer to the mirror. Starting from way out at infinity, the image is tiny, highly diminished, and real. As you step closer to C, the image grows. When you are exactly at C, the image is the exact same size as the object. Keep moving closer, and the image gets enlarged. But, and here is the real magic trick, when you push that object extremely close, right between the pole and the focus, suddenly the image flips. It becomes enlarged, virtual, and erect, forming completely behind the mirror.
Okay, on to part 3, mirror formula and magnification.
Let's transition from drawing shapes to calculating actual distances. We need some math to prove our drawings are right. Now, please don't let the phrase new Cartesian sign convention intimidate you. If you know the basic XY coordinate graph from your math class, you literally already know this rule perfectly. Just place the pole of the mirror right at the origin, 0, 0. The principal axis, that's your x-axis. Anything in front of the mirror, over to the left, is negative. Anything behind it, to the right, is positive. Anything pointing up above the axis has a positive height, and pointing down below is negative.
Boom, that's the whole rule. And here is your toolkit for solving any numerical problem in this chapter. Your mirror formula is 1 over v plus 1 over u equals 1 over f. In this formula, u is your object distance, v is your image distance, and f is that focal length. Then we have magnification, or m. This simply tells us how much the image blew up or shrank down. It's just the height of the image divided by the height of the object. Alternatively, you can calculate it as m equals negative v divided by u. And hey, if your math spits out a negative magnification, that just proves you have a real upside-down image sitting below the axis.
Let's take a quick breather and test our active recall with a couple of classic textbook questions. First up, if a mirror's radius of curvature is 20 centimeters, what is its focal length? Well, since we know r is exactly twice f, f simply has to be 10 centimeters. Easy, right? Second question, why do we absolutely insist on using convex mirrors as rearview mirrors in our cars or on our scooters? Think about it. It's because no matter where that truck is behind you in busy traffic, a convex mirror will always give you an erect, upright, diminished image. This gives you a massively wider field of view compared to a normal flat mirror.
All right, moving into part 4, refraction and the glass slab. So far, we've talked about bouncing, but let's introduce a massive plot twist. What happens when light doesn't bounce off an opaque surface, but actually smashes right through a clear, transparent medium? This, my friends, is called refraction. In the classic rectangular glass slab activity, we literally watch light change its path. When the incoming light enters from the air, which is a rarer, less dense medium, into the thicker, denser glass, it actually slows down. This forces the light to bend inwards towards the normal line. But when it breaks out of the glass back into the air, it speeds right back up and bends away from the normal. Because the top and bottom of the slab are perfectly parallel, that final exiting ray travels completely parallel to the original incoming ray, just shifted slightly over to the side.
That brings us perfectly to part 5, the refractive index. We know light bends, but in physics, we need to know exactly how much it bends. And for that, we use a vital mathematical concept called the refractive index. Just like reflection, refraction plays by strict rules. The incident ray, the refracted ray, and the normal all sit on the exact same plane. But the second rule? This is the game changer, Snell's law. It states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a fixed constant for any given pair of media. This constant value, sine I divided by sine r, literally gives us a map for the exact extent of the bending.
We call this constant value the refractive index, usually written as n. Think of it as a speed limit indicator for light. Light travels at an absolute blistering speed of 3 × 10 to the power of 8 meters per second in a vacuum, or in air. It's incredibly fast, but it physically slows down when it hits a denser medium. The absolute refractive index is just the speed of light in air, c, divided by the speed of light in the new medium, v. Because light gets bogged down more in solid crown glass than it does in liquid water, glass has a higher refractive index of 1.52, compared to water's 1.33. The bigger the index number, the more the light is going to bend.
And finally, part 6, lenses and lens formulas. Let's unite everything we've talked about today by exploring spherical lenses. Lenses are awesome because they beautifully combine the curved geometry of mirrors with the bending rules of refraction. A lens is just a piece of transparent material bound by two surfaces where at least one is curved. Much like our trusty spoons from earlier, convex lenses bulge outwards. They are thick in the middle and thin at the edges. These are converging lenses. They gather light rays and bring them together. Concave lenses, on the other hand, curve inwards. They are thin in the middle and thicker at the edges. These are diverging lenses. They scatter and spread light rays apart. Remember those geometric cheat codes we learned for mirror ray diagrams? Well, good news, they adapt elegantly to lenses. We are still using parallel rays and rays traveling straight through the optical center. The only difference now is that the light doesn't bounce off, it refracts completely through the glass. A parallel ray entering a convex lens bends and passes through the focus on the opposite side. For a concave lens, that parallel ray diverges, bending outwards, making it look as if it originally came from the focus on the same side it started on. Naturally, we have some math here too, but don't worry, the formulas for lenses are nearly identical to the mirror ones. You just have to watch out for the negative signs. The lens formula is simply 1 over v minus 1 over u equals 1 over f. See? Just a quick sign change. Lens magnification is positive v divided by u. And finally, we have the power of lens.
The more intensely a lens bends light, the higher its power. Power, represented by P, is just the reciprocal of its focal length in meters. And we measure this power in a special SI unit called the diopter. We have completely built up your conceptual mastery of Chapter 9 today, from mirrors and graphs all the way to glass slabs and lenses. But before we wrap up, I want to leave you with one final, truly mind-bending thought. You just spent this whole explainer using your own biological lenses to watch and understand this material. We just learned that a glass convex lens has a fixed, unchangeable focal length. So, how exactly does the biological lens inside your eye automatically and instantly change its own focal length so you can read a textbook right in your hands 1 second and look way up at a distant star the very next? It's pretty amazing to think about. Ponder that as you keep studying. Thanks for joining me on this explainer. You're going to do great.